The basic function of any air conditioning or refrigeration system is to create and maintain a certain environment. Temperature and humidity have to be controlled to meet specific requirements, but environments differ, and specific requirements will also differ. A refrigeration environment may be anything from a small refrigerator to a large industrial facility, but any air conditioning or refrigeration system will contain the components that are necessary for the vapor compression refrigeration cycle to occur. Even though all systems have these components, there are many different designs that can be used. These various designs help make a particular system appropriate for the needs of the environment created. As a technician, you'll be working on air conditioning and refrigeration systems. You'll be responsible for maintaining and repairing these systems and for troubleshooting problems that may arise. To do your job effectively, it's important that you understand basic refrigeration principles. You should know what a system is supposed to do and how it does it. Since refrigeration applications vary and component designs vary, you'll also have to know the difference between component designs and how these differences affect the way maintenance and troubleshooting jobs are performed. But keep in mind that all vapor compression systems, whether simple or complex, perform the same basic functions and operate according to the same principles. This program will show you some of the ways that components in refrigeration systems can be designed. Let's take a few minutes now to talk about how these variations in component design can meet the needs of a particular type of refrigeration system. As you know, the four basic components necessary for the vapor compression cycle are the evaporator, the compressor, the condenser, and the metering device. In this program, we're going to see two different types of evaporators. In one type, all of the liquid refrigerant is converted to vapor before it reaches the evaporator outlet. A common design is a series of tubes equipped with fins. The tubes contain the refrigerant, which absorbs heat from air or water passing over them. Another kind of evaporator is known as the shell and tube evaporator. Inside this tank are tubes that hold water. The refrigerant contacts the tube surfaces, absorbs heat from them, and vaporizes inside the tank. This program will also cover two basic compressor designs. One kind of compressor operates by means of pistons and cylinders. As the pistons move up and down, refrigerant vapor flows in, is compressed, and is then discharged to the condenser. Another kind of compressor operates by means of a rotating impeller. Refrigerant vapor is drawn into the impeller and compressed by centrifugal force. You'll also see several condenser designs. In this program, we'll focus on water-cooled condensers. We'll see two common designs, a shell-and-tube condenser and a tube-in-tube condenser. Like evaporators, condensers are basically heat exchangers. They provide a place for heat transfer to occur so that the heat absorbed by the refrigerant in the system can be rejected again. Finally, we'll look at several different metering devices. These devices regulate the flow of refrigerant into the evaporator. We'll see one metering device that operates in response to temperature, and one that responds to pressure changes in the system. Another type of metering device physically restricts refrigerant flow. And still another type operates on the basis of refrigerant volume or level. The particular design of a component affects the way that component does its job. This, in turn, affects the way that maintenance may be performed on that component or system. So, as a technician, the more familiar you are with different component designs, the better you'll be at maintaining, repairing, and troubleshooting the systems you'll work on. This program will introduce you to a wide range of refrigeration equipment. Keep in mind that each component in a system does a particular job, but that its design is important to how that job is accomplished. In the next segment, we'll start to look at the components in a refrigeration system in detail. But for now, stop and review. In this segment, we're going to look more closely at the evaporator in a refrigeration system. We could start with any one of the four basic system components, but the evaporator is the place where heat is absorbed from the area being cooled. So let's start with the evaporator. As you know, the evaporator is located in the low pressure side of the system. It's the place where heat is absorbed from the surrounding air or water by the lower temperature refrigerant inside the evaporator. As the refrigerant absorbs heat and vaporizes, the air or water is cooled. Because the refrigerant is at a low pressure in the evaporator, it vaporizes at a relatively low temperature. There are many different sizes of evaporators, and there are different evaporator designs that are used in a wide variety of refrigeration applications. Two basic types of evaporators are commonly used in air conditioning and refrigeration systems. These are the direct expansion evaporator and the flooded evaporator. The direct expansion type depends on supplying the precise amount of refrigerant to the system where it vaporizes and expands. Let's look at a small demonstrator of a vapor compression system to see how a direct expansion evaporator is constructed and how it actually works. These three glass tubes have been placed in the evaporator so you can see what's going on inside. This demonstrator shows only several tubes, but in a real system there may be many tubes, even hundreds in a single evaporator. The evaporator consists of tubes in parallel circuits, commonly called a coil. The vertical parts across the coil are extensions called fins. These fins increase the coil's surface area to permit greater heat transfer. Air may be blown over the coil and fins to maximize airflow and increase heat transfer. The refrigerant flows inside the evaporator coil. It enters the coil through the metering device. In this system, the metering device is an expansion valve, but other types of metering devices can also be used. We'll talk more about some of these later on. So the metering device allows just the right amount of refrigerant in so that the liquid is converted to vapor before it leaves the evaporator coil. The amount of refrigerant allowed in is also the proper amount to ensure that the vapor acquires the specified amount of superheat at the outlet. Near the inlet, there's mostly liquid. As the refrigerant travels through the coil, it picks up heat from the air passing over the outside of the coil. As it absorbs heat, more and more of the refrigerant vaporizes. By the time it reaches the coil outlet, the refrigerant has evaporated and is slightly superheated. This kind of direct expansion evaporator may also be called a dry expansion evaporator because the refrigerant is no longer in its liquid state at the evaporator outlet. In the example that we've just seen, a direct expansion evaporator was used to cool air. But other direct expansion evaporators may cool water or some other liquid. Evaporators that cool water or other liquid may also be called chillers. You should be familiar with both air and water-cooled types of evaporators, as you'll probably be working with them both at some point. Another type of evaporator that chills water or liquid is the flooded evaporator, also called a flooded chiller. They are often used to provide chilled water for air conditioning systems. To see how flooded evaporators differ from the direct expansion type, let's look at a drawing of a typical flooded evaporator. As you can see, this flooded evaporator consists of a tank or shell with a bundle of straight tubes inside it. Notice that the tubes only partially fill the shell. The rest of the space in the shell is for the refrigerant. Although the flooded evaporator in this drawing uses a bundle of tubes, other flooded evaporators may use a single coil instead. In this flooded evaporator, the water that is to be chilled is pumped through the tubes. Liquid refrigerant flows in the shell around the tubes. As the refrigerant absorbs heat from the water being cooled, it boils and vaporizes. The boiling occurs at a low temperature because the refrigerant is at low pressure. As the refrigerant boils, additional liquid enters the evaporator to ensure that all tubes are covered with liquid refrigerant. The refrigerant vapor rises to fill the space above the tubes. It leaves the evaporator at the top and moves on to the compressor. The flooded type of evaporator is quite efficient because of its excellent ability to transfer heat. This is because the entire outside surfaces of the tubes are in contact with the refrigerant. This enables vaporization to occur quickly and continuously. Of course, in all flooded evaporators, there has to be some reliable means of automatically feeding liquid refrigerant in to replace the amount that vaporizes. This is usually accomplished by means of various float valve arrangements. We'll talk about this type of metering device later on in the program. Now let's review what we've seen about evaporators. We saw two types of evaporators, the direct or dry expansion type and the flooded type. In a direct expansion evaporator, all the liquid refrigerant is evaporated in the tubes so that only superheated vapor leaves the evaporator outlet. In a flooded evaporator, the liquid refrigerant covers the outside surfaces of the tubes and vaporizes inside the evaporator shell before going to the compressor. Evaporators may cool air or liquid. If they cool a liquid, such as water, they are usually called chillers. In a direct expansion chiller, the refrigerant is in the tubes and the water flows around the tubes in the shell. In a flooded chiller, this is reversed, with the water in the tubes and the refrigerant around the tubes in the shell. In the next segment, we'll talk about compressors, but stop now and review your text. In this segment, we're going to look at compressors. The compressor is a very important component in any refrigeration system. In fact, it's often called the heart of the system. The function of the compressor is to take low pressure, low temperature vapor from the evaporator and compress it into high pressure, high temperature vapor. This increase in the vapor pressure from compression allows the vapor to give up its heat as it passes through the condenser cooling medium. There are several ways to classify compressors. One is by the way they achieve compression. Another way is by the type of motor they have to drive them. We'll talk a little more about motors later on. Compressors may be of two main types, positive displacement or centrifugal. We're going to look first at the most common positive displacement type, a reciprocating compressor. Reciprocating compressors are used in many domestic, commercial, and industrial applications. I'm going to use another drawing so that I can show you how a reciprocating compressor works. Reciprocating compressors work by means of a piston and cylinder assembly. This is a simplified cross-sectional drawing of a piston and cylinder. A reciprocating compressor may have one cylinder and piston, two, or many. There are two valves, one on either side of the piston, that seal in opposite directions. As the piston moves down, the pressure in the cylinder drops. The pressure in the suction line forces the suction valve open and allows refrigerant vapor to flow into the cylinder. The suction valve may also be called the intake valve. During the downstroke of the piston, the pressure in the discharge line holds the discharge valve closed. Now the cylinder space is filled with refrigerant vapor. As the piston moves up again, it compresses the vapor into a smaller space at the top of the cylinder. Now the pressure in the cylinder holds the suction valve closed and causes the discharge valve to open. As you may know, the temperature of the vapor is raised as it is compressed. This is called the heat of compression. As the piston completes its upward stroke, it pushes the high temperature, high pressure vapor out of the cylinder through the discharge valve to the condenser. Besides compressing the vapor, part of a compressor's function is to keep refrigerant vapor circulating through the system. So let's see how a reciprocating compressor keeps the refrigerant vapor moving. This is a reciprocating compressor that has been cut away so that you can see how it works. This one has 2 pistons and cylinders. Most 2 or 4 cylinder compressors use a side-by-side arrangement of cylinder pairs like this. While one piston approaches the bottom of its stroke and low pressure, low temperature vapor is flowing into the cylinder. The other piston is moving toward the top of its stroke, pushing high pressure, high temperature vapor out. As you can see here, the 2 cylinders work together in an up and down reciprocal action. The compressor must keep the refrigerant moving through the system to ensure continuous cooling. Now you might be wondering what makes the pistons and cylinders in a reciprocating compressor move. In other words, what drives them? Well, as you may have guessed, they're driven by a motor. Part of your job as a technician may involve maintaining and troubleshooting the motor that drives the compressor in your system. So it's important to understand what type of motor and compressor unit you have and how it works. Now let's go back to our cutaway compressor to see how the motor is connected to the pistons in a reciprocating compressor. In a reciprocating compressor, rods, called connecting rods, are attached to the pistons. The connecting rods connect the pistons to a crankshaft, which is connected to the motor. The crankshaft provides a way to change the rotary motion of the motor to the reciprocating or up and down motion of the pistons. The reciprocating compressor and motor that we've seen here is called a SemiHermetic compressor unit. The name SemiHermetic refers to the fact that the compressor and motor are sealed inside the compressor housing, but with access provided to permit servicing in the field. There are also hermetic and open compressor motor units. In a hermetic compressor motor unit, the motor is sealed inside the compressor housing. It operates within the refrigerant atmosphere. There is no external shaft or shaft seal. Hermetic compressors do not permit access to the moving parts and so are not field serviceable. The other kind of compressor motor unit I mentioned is the open type. Open refers to the fact that the compressor is connected to an external drive motor by a shaft that extends through the compressor's crankcase. Open designs are accessible and permit the motor and compressor to be serviced in the field. The semi-hermetic compressor and motor units are the most common type used in refrigeration and air conditioning applications, and the type that you will probably work on most often. By now you should have a pretty good idea of how a reciprocating compressor works in a refrigeration system. Of course, to operate properly, this type of compressor must be constantly lubricated and cooled. There's information about compressor lubrication and cooling in your text. Be sure to read it before going on. In the next segment, we're going to see a different kind of compressor. But for now, let's review briefly. We saw that a reciprocating compressor operates by means of a piston and cylinder assembly. Refrigerant vapor from the evaporator flows into the cylinder on the piston downstroke. As the piston moves up, it compresses the vapor into a smaller space. This raises both the pressure and temperature of the vapor. Reciprocating compressors are driven by motors. In a hermetic compressor, the motor is sealed inside the compressor housing and is not accessible. In a semi-hermetic compressor, although the motor is inside the compressor housing, access is provided to permit servicing in the field. In an open compressor, the motor can be serviced independently of the compressor. Stop now and review. Be sure to read the additional information in your text before going on. In this segment, we're going to look at another compressor. This one is a centrifugal compressor. Like the reciprocating type that we just saw, the centrifugal type compresses refrigerant vapor to raise its pressure and temperature for the condensing phase. But it does this in a different way. Because its action is different, a centrifugal compressor's design is quite different from a reciprocating compressor. As its name indicates, a centrifugal compressor operates by a rotating or spinning action to produce centrifugal force. This force is used to compress the refrigerant vapor. Let's look at a drawing to see how a centrifugal compressor affects the refrigerant vapor. This is a representation of the impeller in a centrifugal compressor housing. The impeller is an important part of the compressor. It makes the vapor move. It's a large disc that's equipped with a number of radial blades. This blade arrangement is the impeller. It's located inside the compressor housing at the intake nozzle. The impeller spins or rotates very fast. It can be driven by an electric motor or a steam turbine. For now, to clearly see what happens to the vapor as it flows through, we won't have the impeller spinning. Let's trace the path of the vapor through the impeller. We'll show the path of the vapor step by step. As the impeller spins, the vapor travels along the blades from the center outward. As the velocity or speed increases, the kinetic energy of the vapor increases. The vapor is thrown off the blades by centrifugal force and is then forced against the casing. As the vapor moves toward the discharge port, it passes through the wider part of the casing. Here, as the vapor expands, it slows down. This decreases its kinetic energy, but this energy is converted to pressure so that the vapor pressure increases as required for the condensing phase of the vapor compression cycle. As the vapor pressure increases, its temperature also increases. So high pressure, high temperature vapor leaves the discharge port of the compressor and moves on to the condenser. A centrifugal compressor may have more than one impeller. It may be designed with several impellers through which refrigerant flows in series. For example, if there are two impellers, this is called a two-stage compressor. Let's see how this would work. This is a two-stage centrifugal compressor. In a compressor like this, with more than one impeller, the discharge vapor from one impeller enters the suction intake of the next one. Let's follow the flow path of the refrigerant vapor through this centrifugal compressor to see how a two-stage compressor can increase the vapor pressure. As the vapor moves through the first impeller, its pressure increases by a certain amount. As it passes through the second impeller, or the second stage of compression, the pressure increases further. This results in a highly compressed vapor leaving the compressor. Centrifugal compressors are large capacity units. They're usually used for capacities over 100 tons up to several thousand tons, since they can handle large volumes of refrigerant vapor more efficiently and economically. Because the requirements of a system and the demands on a system may change, the amount of vapor flowing through the compressor may not always be the same. We may sometimes need to control the load on the compressor when the system is not operating at full capacity. In other words, we need a way to maintain stable compressor performance when the load may be much less than the full amount the compressor can handle. Shutting the compressor motor on and off for capacity control is not efficient or economical in large centrifugal compressors. These motors are large, and constant on-off operation may shorten their life significantly. One way that compressor capacity can be reduced efficiently while maintaining stable performance is by means of adjustable dampers mounted in the compressor intake nozzle. Let's go to another drawing to see how these work for capacity control. The dampers can be mounted in front of the impeller of a centrifugal compressor, like this. Together, they're called a variable inlet guide vane. Variable because they are adjustable. They can pivot to change position. Inlet because they're located at the inlet where refrigerant vapor enters the impeller. And they are basically guide vanes, since they guide the flow of vapor by providing a specific flow path to the impeller. When the guide vanes are open, large amounts of refrigerant vapor can flow into the impeller. But when the guide vanes move from the fully open position toward the closed position, the space between them decreases. This restricts flow and causes a pressure drop. This decreases the total amount of vapor that can flow in, but the compressor can continue to operate steadily with a reduced amount of vapor. In this way, the compressor's operation is controlled and its stability maintained in spite of a decrease in the load. But the guide vanes also have another effect. Because of their position in front of the impeller inlet, the variable inlet guide vanes cause the incoming vapor to spin. The vapor spins in the direction that the impeller rotates. The spinning vapor pushes the impeller around. This is called the pre-rotation effect. It reduces friction and the power required to turn the impeller, thereby helping to keep the compressor operation stable. Now let's review what we've seen about centrifugal compressors. A centrifugal compressor operates by the rotating action of an impeller to produce centrifugal force. This force compresses the refrigerant vapor to raise its pressure and temperature. There can be more than one impeller in the centrifugal compressor. If there are several, the vapor leaves the discharge port of one impeller and enters the intake port of the next one. Centrifugal compressors are large capacity units and operate at very high speeds. If the load decreases, variable inlet guide vanes can stabilize the compressor's performance. These guide vanes, operating like dampers, concentrate the flow of refrigerant vapor into the impeller so that the compressor operates steadily and efficiently with a reduced quantity of vapor. Stop now and review. Be sure you understand the differences between reciprocating and centrifugal compressors. We're ready now to move on to the next component in a refrigeration system. We've seen evaporators and compressors, so now we're going to take a look at condensers. The condenser is located in the high pressure side of the system. As you'll recall, the function of the condenser is to change the high pressure, high temperature vapor from the compressor into a high pressure liquid. In the condenser, heat that has been absorbed by the refrigerant in the evaporator and increased in the compressor must be transferred to some other medium. As you know, this medium may be either air or water. You'll remember that we used an air-cooled condenser on a demonstrator to show you the basic condensing process. But we're going to be concentrating on water-cooled condensers, since they are commonly used in industrial and commercial applications. In this segment, we're going to look at condensers that are cooled by water. Some other condensers that are cooled by air are discussed in your text. Be sure to read this additional information carefully. Like evaporators, condensers are heat exchangers. The condenser provides a place where heat exchange can occur to transfer heat from the superheated refrigerant vapor to the cooling water. As a technician, part of your job will be to maintain the condenser so that proper heat transfer can occur. The first condenser design we're going to see is a shell and tube condenser. It's the most common type in large systems. Let's look at another illustration. As you can see, the shell and tube condenser is quite similar to the shell and tube evaporator we saw earlier. It consists of a cylindrical housing or shell that contains a bundle of parallel tubes. As with the flooded evaporator, the tubes in the shell and tube condenser only partially fill the shell. The space at the bottom is a receiver for the liquid refrigerant. In this condenser, the cooling water flows inside the tubes, while the hot refrigerant vapor flows around the tubes within the shell. In the condenser, water is pumped through the tubes through these inlet and outlet connections on the shell end plate. In this example, the water makes 2 passes through the condenser. In other designs, the water may make 1 pass or as many as 4. Hot refrigerant vapor enters the condenser shell at the top and flows around all the tubes. As the vapor comes in contact with the cooled tubes, it condenses on the outside tube surfaces. The droplets of refrigerant liquid fall off the tubes down to the bottom of the condenser. As cooling continues, the refrigerant is subcooled, but it is still at high pressure. The bottom part of the condenser shell may be used as a receiver for the storage of the liquid refrigerant. When refrigerant is needed in the system, it flows out of the condenser receiver into the liquid line and back through the metering device to the evaporator. The condenser must be able to do 2 things. The condenser must quickly condense all the high-pressure, high-temperature vapor to a liquid, and it must be able to provide a continuous supply of subcooled liquid to the metering device at the evaporator inlet. Now let's look at another example of a water-cooled condenser. This one is called a tube-in-tube condenser. It's used primarily in smaller size units. This one is really a combination air and water-cooled unit. Let's see why this is true. In this type, the refrigerant flows through the outer tubing. The cooling water flows through the inner tube in the opposite direction. The refrigerant is cooled by the water circulating inside. The refrigerant is also exposed to the additional cooling effect of air flowing naturally over the outside of the outer tube. These 2 cooling effects occur at the same time, so this condenser really is an air and water combination. Well, we've seen 2 different types of water-cooled condensers used in refrigeration systems. Another common type of condenser is the shell and coil condenser. Be sure to read about this type in your text. Some of the characteristics of these designs are discussed in your text. These characteristics include a component's efficiency and methods of cleaning and maintenance. You should be able to recognize the most common condenser designs and have some idea of the servicing needs of each type. As I mentioned earlier, there are many more types of condensers than the ones we've looked at briefly here. Some condensers are completely air-cooled, and some are cooled by the evaporation of water. But now, let's take a minute to review what we've seen in this segment. In a shell and tube condenser, the cooling water flows inside the tubes. Refrigerant vapor flows around the tube. As the hot vapor comes in contact with the cool tubes, it condenses and falls to the bottom of the tank. In a tube-in-tube condenser, refrigerant flows through the outer tube and water through the inner tube. The refrigerant vapor is cooled both by the water and by air flowing naturally over the outside tube surface. Stop now and review these condenser designs. So far, we've seen three of the major components in a basic refrigeration system: the evaporator, the compressor, and the condenser. Now we're ready to talk about the metering device. As you'll recall, the metering device controls the flow of refrigerant into the evaporator. In any refrigeration system, there has to be a way of regulating the flow of high-pressure liquid refrigerant into the evaporator. Remember, when the refrigerant leaves the condenser, it has changed to a liquid, but it's still under high pressure. The refrigerant liquid flows through the liquid line to the metering device and the evaporator. But as you know, the refrigerant is under low pressure in the evaporator. So how does it change from high to low pressure? By means of the metering device. It might help to think of the metering device as a dividing point in the system between the high and low pressure sides. Metering devices can operate in response to temperature, pressure, or volume. Let's look at one kind of metering device that responds to temperature. It's a very common type used in refrigeration systems. This is a typical thermostatic expansion valve. It has been cut away so you can see inside. The thermostatic expansion valve maintains a constant degree of superheat by regulating the flow of refrigerant to the evaporator. This valve has a thermal sensing bulb that is mounted on the suction line to the compressor at the evaporator outlet. The bulb is filled with the same refrigerant that is in the evaporator. It senses the temperature of the superheated vapor leaving the evaporator. How does this thermal bulb coordinate with the valve to control the flow of refrigerant to the evaporator? Well, let's look at our valve and see. The temperature of the vapor leaving the evaporator coil is sensed by the thermal bulb on the suction line. If the outgoing vapor is superheated too much, the bulb pressure on the top of the valve diaphragm will increase, and the valve will open to let more refrigerant into the evaporator. As more refrigerant is vaporized, the degree of superheat at the outlet will decrease. But if the outgoing vapor isn't superheated enough to the specified degree, the spring pressure and evaporator pressure under the diaphragm will be stronger. The valve will then close to restrict the amount of refrigerant entering the evaporator coil. This will decrease the temperature and pressure in the evaporator and will result in a greater degree of superheat at the outlet. So the thermostatic expansion valve controls the flow of refrigerant in direct response to changes in temperature. It's a direct acting valve. Now let's take a look at another type of valve that operates in response to pressure. This is an automatic expansion valve. It's also called a constant pressure expansion valve, since it maintains a constant pressure in the evaporator regardless of the load on the system. It's actually a reverse-acting pressure-reducing valve. The automatic expansion valve operates by means of a diaphragm or bellows and a spring. This one has a diaphragm. It's activated by the pressure in the evaporator, which pushes against the bottom of the diaphragm. The spring exerts a force on the top of the diaphragm. When the evaporator pressure increases, the diaphragm moves up, overcoming the spring pressure and closing the valve. This reduces the flow of refrigerant into the evaporator coil. If the pressure in the evaporator decreases, the spring force will be stronger and the valve will open to admit more liquid. This raises the pressure in the coil again. The spring in this kind of valve can be adjusted for operation over a wide range of pressures and with different refrigerants, so it's a very versatile metering device. You may be wondering what can cause the pressure in the evaporator to change. Well, load changes on the system affect the suction pressure into the compressor. This, in turn, affects the pressure in the evaporator coil, which activates the automatic expansion valve. Because the valve's action holds the evaporator pressure steady in spite of changes in load, the compressor tends to operate more steadily. That's one reason why the automatic expansion valve is commonly used in smaller systems where the load is relatively steady. This valve is not as suitable for continuously running compressors that operate under variable loads. Because of its reverse action, the valve may tend to starve or flood the evaporator as it tries to maintain a constant evaporator pressure. The valves we've just seen are two kinds of metering devices used in refrigeration systems. Remember, they control the flow of refrigerant liquid in order to maintain a constant low pressure in the evaporator so that heat can be absorbed from the surrounding air. Now let's take a minute to review. The thermostatic expansion valve responds directly to temperature changes. It has a thermal sensing bulb that is mounted on the suction line to the compressor at the evaporator outlet. The bulb senses the temperature of superheated vapor leaving the evaporator. If the degree of superheat of the vapor is too high, the valve will open to let more refrigerant into the evaporator. If the degree of superheat is too low, the valve will close to reduce flow into the evaporator. The automatic expansion valve responds to changes in pressure inside the evaporator. It opens to increase the flow of refrigerant when the pressure decreases. It closes to decrease flow when the pressure increases. In the next segment, we're going to see some more metering devices. But for now, stop and review the operation of the thermostatic expansion valve and the automatic expansion valve. In this segment, we're going to see two other metering devices. In the last segment, we looked at two types of expansion valves that are used as metering devices. But not all metering devices are valves. One in particular is extremely simple. It's called a capillary tube. This is what a capillary tube looks like. As you can see, it's just tubing with a small diameter. It has no moving parts. And it can be cut to various lengths to create the desired pressure drop between the high and low pressure sides of the system. The capillary tube reduces pressure by restricting the flow of the refrigerant through the liquid line from the condenser to the evaporator. It is designed so that just enough liquid flows through to replace the amount that is vaporized in the evaporator while the compressor is running. This metering device is usually not used in large commercial applications that may have widely varying loads. It's used primarily on small systems that have more constant loads. You should be aware of the capillary tube. Since it's so common and so simple, you're sure to come across it at some point. The main problem that may occur with capillary tubes is that they may become clogged or blocked. Part of your job may involve cleaning and maintaining them to ensure the correct flow of refrigerant through the liquid line. There's another type of metering device I'd like to tell you about before we leave the topic. It's called a float. Like other metering devices, floats also serve as a dividing point between the high and low sides of the system, and they also meter or control the flow of refrigerant into the evaporator. Floats are usually used with flooded evaporators and can be located either in the high pressure side of the system or the low pressure side. The design of this float mechanism is similar to those used in refrigeration systems. It's actually an automatic valve that's controlled by this spherical part, the float. The float is connected to a lever or mechanical linkage. As the level of liquid refrigerant changes, the float rises or falls to open or close the valve. This little demonstration was just to give you an idea of how a basic float mechanism works. As I mentioned, there are two types of floats used in refrigeration systems: high side floats and low side floats. The two kinds of floats are similar in function and design, but one controls liquid level in the condenser and the other controls the level in the evaporator. As a technician, you'll need to know the differences between these types. Let's look at a simplified drawing of a high side float so you can see how liquid level is actually controlled. A high side float is located in the high pressure side of the system, usually in the condenser. When the compressor is operating, refrigerant liquid from the condenser flows directly into the evaporator. As the liquid level in the condenser rises, the float also rises. Since the float is connected to the valve, it pulls the valve away from the valve seat as it rises. This permits the liquid refrigerant to flow directly into the evaporator. As the liquid level decreases again, the float moves down and closes the valve to reduce or stop flow. During normal operation of the system under a steady load, the float and valve stabilize at the appropriate throttle position to maintain the required constant flow into the evaporator. The high side float control sends liquid to the evaporator coil as fast as it's condensed. This means that most of the refrigerant for the whole system is always in the evaporator. There's no other place for the refrigerant to be stored. So in a system with this type of metering device, it's important that the refrigerant charge, or the total amount of refrigerant for the system, is exactly the right amount to maintain the proper level in the evaporator. If too much refrigerant were put in, all the liquid wouldn't vaporize in the evaporator, and liquid could get into the compressor. This would damage the compressor. Too little refrigerant in the system would cause the float valve to stay closed and not fill the evaporator. Thus, the system would not cool adequately. Well, we've seen the high side float, but some systems may use a low side float. This float is located inside a flooded evaporator. The lever and linkage mechanism between the float and the valve are connected in an opposite way, so that as the float rises, it closes the valve to stop the flow of refrigerant into the evaporator instead of opening it to permit flow. And as the float lowers, the valve opens. The other major difference between low and high side floats is that the low side float receiver is large enough to store all the refrigerant for the system and some extra. So it functions both as a metering device and as a liquid receiver. Well, we've seen three different types of metering devices that can be used in refrigeration systems. First, we saw two valves, one responding to temperature and one to pressure. Then we saw a capillary tube and a float arrangement. Even though all of these devices are very different from each other, they all do the same basic job: to maintain the correct pressure in the evaporator so that the refrigerant can vaporize at a low enough temperature to absorb heat. As heat is absorbed from the area surrounding the evaporator, this area is cooled. In this program, you've seen quite a lot of refrigeration equipment. There are even more variations than we've had time to show here, but you've seen the common equipment used in both large and small refrigeration and cooling applications. As a technician, you'll work on many different systems. Each one will have a particular set of requirements and a particular design, so you should be familiar with the range of possibilities that you might encounter. This training program has been general in nature. When operating and working on any equipment in your plant, be sure to follow the procedures provided by your facility and the equipment manufacturer. If you have any further questions, talk to your instructor or your job supervisor, and always use the best safety practices when doing any work.